Welcome to Code 733Z. In today's video, we will take a deep dive into a hybrid variational autoencoder and Cox proportional hazard model, also known as HVAE-COX. We will be using the lung dataset to demonstrate how this model can be used for survival analysis. We will start by understanding what the HVAE-COX model is, then explore the dataset and finally go through the Python code line by line to ensure you grab every concept. By the end of this video, you will have a solid understanding of how to implement survival analysis using deep learning. So let's get started. What is the HVAE-COX model? The HVAE-COX model is a hybrid approach that combines variational autoencoder VAE, which are used for learning latent representation of input data while reducing dimensionality. Cox proportional hazard Cox PH model, a widely used method for survival analysis that estimates the effect of features on the time until an event occurs, such as death or failure. The advantage of this approach is that it leverages the power of deep learning to capture complex feature representation while incorporating the Cox model for survival prediction. Essentially, the way helps us learning meaningful latent features, which are used to estimate risk scores via the Cox model. Understanding the lung dataset. The dataset we are using is the lung dataset, which is commonly used in survival analysis. It includes data on lung cancer patients and contains various features related to their health condition. Key features in our model: age, weight loss, meal calorie, pH corner, target levels, time, and status. We progress the dataset by standardizing the feature values and converting them into tensors suitable for deep learning models. Now, torch.nn and torch.nn functional used to define and train deep learning models. Adam optimization algorithm for training. Pandas and NumPy for handling data. Lifelines, a Python library for survival analysis used for loading the lung dataset and evaluating the Cox model. A standard scalar used to normalize data for better model performance. Encoder network. The encoder compresses the input features into a latent representation, uses ReLU activation to introduce nonlinearity. Decoder network. The decoder constructs the input data from the latent space, uses sigmoid activation to constrain output values between 0 and 1. HVAE-COX model. Reparameterized trick is used to enable backpropagation through a stochastic node. Latent variable Z is sampled and passed to the decoder for reconstruction. Defining Cox loss function. Compute Cox negative log likelihood loss to measure survival risk. Training function combines VAE loss, reconstruction plus KL divergence and Cox loss for training. After all that, you can see the output. This is the Z index or C index number. Okay, we covered everything from theory to implementation. If you found this video helpful, like, subscribe, and leave your question in the comment. See you in the next video on Code 733Z.